probability. Okay, so welcome to the fourth class of our big data analytics. Okay, so what I'm going to do is to let me take you first to the class syllabus, right? So as you can see, we spent the first week to the concept of big data or data science, big data or data analytics, whether or not it's big data or not big data. Again, I stress that big data has three main features. One is the fact that it's big, large volumes, right? Another aspect is the velocity. It comes to us fast. We have to deal with it fast. We have to give response fast. Those are more or less kind of engineering, software engineering related. And so you would need like a big data platform, like distributed processing and memory and so forth. So those are not really amenable to class teaching per se. Plus, if you work on a real big data platform, it's going to be a different kind of training for different systems they have anyway. But the aspect that we are going to focus on is the third D, which is the variety of data.
อาจารย์ครับ
Okay, sorry. Okay, I've been speaking in silence. So okay, so back to what we were talking about. We are going to be working again with big data with respect to the variety of data. Having said that, the bulk of analysis, which is like the second part of the title of this course, analytics, will deal with numerical data or categorical data that basically comes into a tabular form. So you can think of it as Excel-like, okay, Excel-like, except more powerful and more general than Excel data. But it's that kind of thing where you have a bunch of data, okay, pertaining to your clients, pertaining to your patients, pertaining to your subject studies, and then you have different attributes in columns, different measurements, and you want to analyze that. Okay, you want to analyze that. Now, the first thing we do is we sort of like try to visualize, get a good feel. Now, last week we started with data visualization. Okay, data visualization, and this week we are going to statistical description and go into probability and statistics. Now, this is a little bit different from history, by the way. because imagine, yeah, now you communicate. I want to say, what does the data look like? What does the data look like? I would do something like, let's go to here. I'm sharing the screen, correct? Yeah. So let's say, yeah, you see the screen, okay, right?
Yeah, yes, we can see the screen.
So let's say, let me go back to down here a little bit. Okay, let's say I have some kind of data. I have some kind of, let me show you a good set of data. Okay. Okay, so this is a data that's from an example class from Mathematica. So let me load that. Okay, I'm just loading it. Okay, so again, this is a data that comes in tabular form. Now, here's the deal. Nowadays, the first go-to tool is histogram. Okay, the first thing we do is actually plot histogram. And this is very common sense. It tells you, okay, first of all, from looking at this, let's say I'm plotting what's called Old Faithful duration. Okay, do you guys know what Old Faithful is? Have you guys been to Yosemite Park in the United States? Oops, I don't know if we're going to have this. You know, the whole purpose of me driving all the way here to July, because I kind of assume that the network is a little bit more stable. But today, I think they're having problems. Anyway, well, this is what an old faithful looks like. Yeah. Now, so somebody sits by the side and record how long it lasts. Records how long it lasts. And so this is it. This is how the histogram of how long it lasts. You see that there are kind of two groups. Sometimes it lasts around 2 minutes. A lot of time it also lasts around 4 and 5 minutes, but nothing in between. So this is kind of weird, right? But it's a feature that you immediately detect from looking at it.
Excuse me, ครับอาจารย์ I don't think you're sharing your screen anymore.
Oh, okay. Let me share screen. Okay, how's that? Yeah. Yes. Couple, hello. Can you see now?
Yeah, we can see it.
Yeah. This is Yellowstone. Sorry, not Yosemite. Yellowstone National Park, the Old Faithful. Okay, every now and then, every couple of 10, 20, an hour or so, it erupts, and somebody sits by the side and records how long the eruption lasts. Okay, so you record that in tabular form, basically. So what we did was we imported this. This is called Old Faithful. Okay, now I'm plotting the duration, just the duration, how long it lasts, and you will see that the histogram indicates that there's a lot of time when the hot water, the geyser spout for about 2 minutes duration. So this is minutes. Okay, so about 2 minutes, but also quite a few last like 4 or 5 minutes. But for some reason, you don't have something in between. So it's kind of suggesting that there are actually two different processes or different pockets. A small pocket would have less water, so it would spout water for about 2 minutes before it runs out and then start accumulate. Now, if the big pocket accumulates and bursts, then it's going to last a bit longer, so like 4 or 5 minutes. So this suggests to you, without any kind of modeling, that maybe there's underground pocket, two sides of pocket. There's a small pocket, there's a big pocket, a big cavity, right? Store different amounts of water, or maybe different channels, but definitely two different ways. Well, this is common sense to us now. The way we look at the data is to plot the histogram first. But you can imagine that, let's say in the old days, okay? Now I want you to imagine that back in the day, you can't send picture in line, okay? Let's say you want to communicate with someone long distance. The old day would be like telegram, okay? In the modern day, it would be line. Now let's say line version 1.0, you can't add picture. You can only add words. So you certainly cannot communicate something like this, right? You can't send a picture, you can't send a histogram. You certainly don't want to send the whole data set, right? So what makes sense is to get some kind of summary, okay? And that's what statistical description is all about, okay? So now we're working kind of backward, right? Because we have the technology. We said the first thing we get the data, we plot the histogram. Okay? But you can imagine in the old days, they start differently. They'll start with the statistical description. Okay? The first obvious statistical description is average, right? An average. So likewise here, you would take maybe the total average. It turns out the total average may be something like 3.5 minutes. Okay, but that's actually misleading. But you didn't know that because all you can do is take an average. So right away, you can see why, if you just blindly take data set and apply statistical description, common sense tell you the first summary is an average. Doesn't give you the whole picture because there are actually two kinds of average. There's kind of average for the small pocket and there's an average for the large pocket. So that's the first lesson you should have today, is that statistical description is limited. It's useful in certain cases. Now, and we'll go into details of that. Okay? So think of statistical description as you get a whole bunch of number, 1,000 number. You can't text 1,000 number to your friends, and you want to tell your friends, what you're taking a vacation. You can't take a picture, you can't send a picture, but you can say, you're at the site of the old geyser, the old faithful. And your friend asks, what is it like? How long does it last? And you would take measurement. Okay, maybe you sit around all day and you take 100 measurements. And then you say, well, on average, it lasts about 3.5 minutes. But that's actually misleading because there's actually pockets of around 2 minutes and pockets of around 4.5 minutes. That's it. Okay, so right away, you see that we're working with a lot more powerful than we had before all this, computational graphic becomes a commonplace. Now it's common. And last week, all I wanted you to do was to use this histogram function. Okay, histogram function has a default number of bins. Did that. Okay, so this is the sort of thing we're working with. Now, from statistical description, we'll go to probability and this statistics model. So let me just go ahead and jump in. Okay, then we'll move to linear algebra and calculus. If you can't finish all that today, we'll extend a little bit to next week. That's okay. But you need certainly linear algebra and calculus quite a bit when you go to machine learning. Okay. So if you recall our syllabus, if you recall our learning program, we have data analytics, using statistical method and machine learning. Statistical methods, you presumably had a bit of that in year one, so we're going to just cover it today and probably refer to it. I will not teach you much more. But the machine learning, certainly I have to teach you from scratch. Okay, and machine learning is what requires linear algebra and calculus. So that will be the subject of the second half of today, as well as maybe the beginning of next class, if we don't get to finish everything by today. Okay, so let's go to probability and statistics. Now, your TA told me that some of you had tough time following the lecture. So I don't want you to just focus on what's on the Zoom screen. I want you to actually start this notebook and follow through. Okay, so maybe you can make the Zoom screen sort of like a smaller half, but you should be focusing on this thing. You should be focusing on following this. If you can follow this, that's the whole purpose. Okay, right. So let's get started. So what do we mean by statistics? Obviously, we don't mean things like sports statistics, right? That's kind of like personal achievement. Okay, we want statistics on events, on things that happen. You know, you can say something like, what's an average duration of a pandemic in the past? You look at the Great Spanish Flu pandemics of 1912, okay, which by the way didn't start in Spain. It just happened to be that Spain wasn't in the part of World War II, so it was not hidden as a wartime secret. So they call it Spanish flu. You look back to the plague, right? So it's in the Middle Age and so forth. Okay, and then you have this thing called population statistic, and this is where most of your statistical work will be all about, because you can think of population as everybody in Thailand, or you can think of population as everybody who potentially is a client to your product. Okay, so population ประชากร doesn't mean the whole country. It can also mean just a segment, particular target group, client group. Okay, and finally statistics as as numerical visualization. So this is where we talk about that histogram thing. Okay, so statistical measure. Now these are, think of measure as what? Numbers, right? You measure in numbers. You take the tape measure and say, how long is this? Instead, you use statistical measure. You say, oh, how widespread it is. How much is it on average? How big, how wide, how short, how small. These are all numerical values, right? And you can do that on even non-numerical data, but we'll talk about it, okay? So the first thing you focus on, and again, I'm going to go very quickly because a lot of this should have been in your statistical 101, okay? I'm just going to emphasize on the element that you will really focus on. So you have measure of central tendency, right? Of central tendency. So you have the means. You know how to do that, right? Means is you take the sum and divide. What's a median? Median is you line your data up from the largest to the smallest, and you take the one in the middle, and you talk about the mode, which is the value that happens most often. Okay, so going back to this data that we saw earlier. Collapse this. And then we go to this guy. Okay, we'll go to that in the later half. Just a second. Okay, this, right? You take all this and an average. An average is like, this would be some kind of wave. This would be some kind of wave, right? So this is very tall. That means it's very heavy. It's the same, made of the same material. And you're trying to put some kind of fulcrum. So wherever that fulcrum is, that is the mean. Okay, so mean of all faithful data duration is equal to 3.48. So it's about here. It's about here. So if you put a fulcrum here, it would not tip to the left or the right. It's just the right balance. Okay, that's called the mean. Now, what is the mode? Well, if you take the mode, that means all this data, however many data points there is, let's see, length. Okay, 272. So 272 eruption. You take the longest and the shortest, and you line up, and you go to 136 and 137, and you average that. Oops. is mode is a quantile of 50%. Is 4. It's 4. It's actually here because there's a lot of people here. So if you line up from the shortest to the longest duration, the 136 is around 4 minutes. Okay. And so that's defined as median and so forth. Whereas the mode is the most often value. So that's sort of like this one or that. So you can see that this one is called multimodal because it has 2 humps. Okay. So let's go back. Okay. So we have mean, median, and mode. But knowing where the middle is not enough, right? Let's say you want to sell a hat, and the average circumference is, say 15 inches. And if everybody has the same size hat, you can only just make one size, that'd be good enough. But if you have small head and big head, then you have to make many sizes. You want to know how wide the dispersion is. So that's why you have this. Measure dispersion range quantile, okay? So that the details of how you calculate this should be covered in your year 101, okay? Now, skewness is different. Skewness means that if you look at your distribution, does it taper to the right and to the left? And kurtosis, that's relative to normality. I'll talk about that later. But what do we mean by, what do we mean by skewness and kurtosis? I suggest the easiest thing is to say skewness, Wikipedia, and that has all the things you need. Obviously, this thing here means you are skewed to the right. Okay, skewed to the right. Okay, for this one, skewed to the right, it's a positive skew. Okay, so likewise, when we go to kurtosis, okay, kurtosis is how spread out. So if you want to make a few size hat, you would prefer that your head population does not have too big a kurtosis. If you have bigger kurtosis, you have to make many different sizes. You have to make small hat, very small hat, all the way to very big, gigantic hats. So kurtosis is a measure of how wide it is. So I'm going to just mention that. So all these here, okay, that I'm just briefly mentioning, that's covered in your probability and statistics 101. Okay, just remember that because you will need to report that, even though you can put the picture nowadays, right? You can report with histogram and picture. The first thing you would do would also be this. Okay, so let me write down in the side note. Okay. Just write this as histogram gives you a picture of how your data is, your numerical data is distributed. Okay. Statistical measure, okay, give you a summary number. Okay, gives you summary number. Describe, okay, the data. Okay. Now, so you have central tendency, you have dispersion, okay, and you have skewness, and D, you have kurtosis. Now you will probably report this. So the first thing you do, okay, and this is how you would do with your project as well. The first thing you get the data. So the first thing you get the data would be do this, histogram and basic statistical measure. Okay, this is just a description. This is just a description. This is just a description. Now, so this is not probability yet. So let me back here. Okay. So this is what we call descriptive. Okay, this is okay because it describes, it summarizes. Okay, this is what we call descriptive statistics. Okay, now two, there to make some kind of prediction. Okay, you need a model of how your data in general is distributed. Okay, in other words, based on a sample data, you make inference on how the population data looks like or would look like. Okay, so in other words, for example, okay, how tall are Thai people? Okay, you would say gather 100 Thai people, take an average. Okay, then make that your guess. That's it, simple as that. Okay, now notice, I want everybody to pay attention. There are three parts to this, right? Part one, how tall are Thai people? That is the inquiry, right? That's the query that you want to know. Gather 100 Thai people, that's your sampling. Okay, query. Sampling. Okay. Method, take an average. Right. Okay, application. Use that to make your best guess. Okay. This has 4 elements, but obviously this is stupid, right? Is there anybody going to do this kind of modeling? There isn't, right? There isn't. So this is still valid because you can ask any question, right? Sampling, to an extent, we're not going to cover that. Okay, that's assuming you have this kind of a method of getting your sample that's not biased. That's kind of like practical and covers the whole large sample as much as you can. Okay, this is where you have this bit here is where you expand. In this class, you can use statistical method and or machine learning tool. Okay, so instead of taking an average height, that's kind of like too naive, too simple, right? In this class, you can use statistical method or machine learning tools. Okay, now statistical method is here. In order to probability model is how you would describe the histogram with mathematical. That's it. That's it. I want you to think, okay? Now, some of you may have more sophisticated training in probability and statistics. That's good. That's good. But fundamentally, I want you to look back and say, you know, all it is I want to draw a mathematical function that looks like the data. Okay? Think of it as a curve fitting. So in this case, this is a little bit hard, okay? This is a little bit hard. But you want to draw a distribution that looks like this, you know? So let's okay. So this is your data, right? So this is your oops. Okay, so this is your histogram, right? What is probability model? A probability model is to draw a mathematical function. Oops. Okay. That best matches your data. That best matches your data. So once you have this in mathematical form, you can do all kinds of analysis on it. You can narrow on this, just this area. You can narrow and say, what about here? What about this? What is it? How likely is it to go beyond this and all that? This is all doable. You can't do this with just a raw data. So think of this as a compression. You have information that pertains to individual duration of all geyser eruption duration. Now, what you want to do, okay, you can send your friend a picture. You can send your friend the mean, the median, the mode, the skewness, the kurtosis, okay? Or, and this is the most powerful of all, you can send your friend mathematical formula. But this mathematical formula is more realistic than this one, right? So you have to learn how to draw the mathematical function. Okay, so that's what it is. Okay, so that's what it is. That's what it is. How would you describe or mimic the histogram of your data with some mathematical function? That's what it means. That's a probability model. Now, and this is where you do this. So in the probability class, you learn, say, 8 or 9 different types of distribution. Okay, so some types, so in other words, in order to draw the picture, that looks like this, you have different choices of function, and you learn about 8 or 9 of them. Okay, that's what you learn in class. Now, in reality, how many of them are there? How many of them are there? Well, out of hundreds, okay, there are hundreds of different functions. Okay. So you're gonna learn 8 or 9 functions. And you're gonna learn 8 or 9 functions. Now, first of all, there are 2 types of probability distribution, one for discrete data, one for continuous. Yeah. So what's a discrete data? Discrete data, does it mean that it has to be a round number? Anybody? Okay, raise your hand if you think that discrete data means that the number has to be a round number, like 1, 2, 3, 4, 5. Actually, it doesn't. It doesn't. It can be. I can have a distribution over 1.7. Okay, that's not the point. The point is that there are finite options. Okay, so go back to definition of set. Okay, go back to definition of set. You have finite set. Okay, and you have, what else do you have? What else do you have? Come on, guys. This is a review. What's bigger than finite set? You have infinite set. Right? Come on. Why are you laughing? You just have finite and infinite set. That's not that funny. Okay? You just have two things, right? Now, infinite set, what do you have? Infinite set, you have countable, bounded, semi-bounded, and unbounded. Right? Right? Okay? So, when I say discrete, I'm talking about finite and countable. Okay? Whereas continuous refer to when the random values belong to set. That's it. Okay. Okay, so two types of probability. Okay, so there are two types of probability, one for discrete data and one for continuous data. So go back to definition of set. We have definite set, finite set, infinite sets. Okay, discrete is for using a discrete probability is used for when the random values belong to finite or countable set. Continuous belong to either bound, semi-bound, and unbounded. So you will see that there are 5 divisions, right? So there's 2 division, 2 major division, and in here there are 2 more division, there are 3 more division. I want you to go to Wikipedia, any page, Wikipedia, and put in something like normal distribution. Oh, doesn't matter, uniform distribution. Just ignore everything above. Ignore everything above. Ignore everything. Oops. Yeah. Ignore everything. Go all the way to the bottom. Okay. Now look at this. This is the probability distribution. So these are the menu. Okay. I told you guys that in your class last year, you should have learned about 8 or 9 or maybe 9 or 10. Okay. Yeah. Out of 100, guess how many you have in Wikipedia? All of these are different. Okay. These are the hundreds that I was telling you about. There are 2 types. The big division is discrete versus continuous. Okay, discrete, continuous. Within discrete, there are two types. Finite, in other words, it's like your dice, right? When you roll the dice, you can take 1, 2, 3, 4, 5, or 6. So that's finite, right? 1, 2, 3, 4, 5, 6. Okay, so that's called finite support. But if you have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to infinity, okay, that's your random number. Your number can be anything from 1 to 2, 3, 4, 5, 6, 7 up to infinity. That is infinite, but it is countable. That is called infinite support. Okay, so you have discrete versus continuous, then you have finite versus infinite. So this versus that. Okay. And continuous, we have three cases. It's bounded on the left side and the right hand side. For example, can be any number between 0 and 1. That's called bounded. That's this guy, bounded. Okay, but if you say something like can be any number greater than 0, any positive number, it's bounded to 0. It can't be lower than 0, but it can go up to infinity. So that's called semi-infinite interval. So that's semi-bounded. Finally, you have distribution that say any number from minus infinity to plus infinity. That is unbounded. So that's this guy. Okay. Now, ignore everything else down here because we haven't got that far yet. Okay. I want you to look with me. Yeah. These are the 8 of 9 you should have learned. You should have learned Bernoulli. You should have learned binomial. You should have learned Poisson. There's Poisson. Okay, 3, right? So again, Bernoulli, binomial, Poisson, 3 of you already. Okay. You should have also learned uniform, 4. That's uniform. You should have learned beta, 5. Okay. So let me list them. Okay. Let me list them. Finite. You should have learned finite. Okay. Bernoulli, binomial. Okay. You should have learned Poisson. Okay. You should learn uniform and beta. Semi-bounded. You should have learned exponential. Gamma would be nice. And you should have learned log normal. And finally, for unbounded, you should learn normal, student T. Student T. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Yeah, these again. This is not a review like a comprehensive review. This is sort of like an indicator. These are the basic you will need in data analytics. Okay? So out of all this, out of all this, I selected for you those that are most useful. Okay, those that are most useful. Okay, these are the most, some of them are a little bit esoteric. Actually, this one is very good. Let me put this as well. Okay. Okay, so this is good. And another thing, if I may, I would have what's called now. If all the probability distribution in life are within this 12, you're in good shape. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? If you know 12 distribution, you are good. You can do data analytics. If you know less than this, you can't. Okay? These are the very basic. Basic. Right. So that's what you need to do. Now, each of these, okay, will fit your data. Each of these will fit your data. They should. Okay. Now, this is all you can do in statistical model. Okay. Everything else follows from here. All the inference, hypothesis testing, the means are equal. Everything is based on getting the right distribution first. Okay. Let me see how that works. Let's see how that works. Okay. So let's say, okay, I'm just going to show you a few, right? Just to make sure you're on the same language. Yeah. This is in your notebook, right? You can play with all this. This is how Mathematica, like Python and a lot of language, is communicated with a functional form. So if you want to know what a distribution is, okay, so if you want to plot, let's say you want to plot a histogram, you want to look at the data, this is the command, okay? So this, for example, say, okay, now let's use both Wikipedia and this together. So let's say I'm going to, which one do you want to play with? Let's say exponential. Exponential is good. Exponential is a nice thing. Okay, you've seen this, right? Raise your hand if you haven't seen it. Okay, you should have seen it. Okay, so this would be something like distribution of waiting time. Okay, so this would be like minutes. Make it a little bit. Okay, this is a distribution of your waiting time. Okay, you're waiting for a bus, school bus. So most of the time, if you take the area under this is the probability that you wait between 0 and 1 minute. Okay. Okay. So, right. So this is the. So let's do this with Mathematica. This Mathematica. Now I have exponential. Okay, let's go to exponential. But we can do it from scratch. I want you to do it from scratch. So let's say notebook. Okay. Type in exponential. Okay. You notice it's a exponential this and that. We want exponential distribution. So it's a distribution, right? It's a distribution. Now this distribution, okay, how does it work? You click F1. This exponential distribution has parameter lambda. Okay, lambda. So let's say I'm going to say lambda. I don't know what, let's see what lambda is. let's say I'm going to set lambda, escape lambda equal to 5, 3. Okay, lambda is equal to 3. And exponential distribution lambda again, I want you to type along, so I'm going quite slowly, deliberately. Okay, I can speed up if you want, but I'm going slowly because I want you to type. Exponential distribution. So that's my distribution. Okay, my distribution. Okay. Right. Now, I don't know what it looks like. I don't know what it looks like. Let's see what it looks like. Okay, let's plot my distribution x from 0 to 10, let's say. Now I can't plot my distribution because I don't know what what do you want to plot? Do you want PDF or you want to plot the CDF? So actually you want to plot this PDF of my distribution okay, I see that. That's my lambda. Where's my lambda? My lambda is 3. Now, anybody want to guess what lambda does? Anybody? Okay, let me give you a hint. Okay, what if I want my distribution? My distribution. One thing. Okay, so lambda gives you 1 over mean. Okay, so instead of doing this, I'm going to say, forget it. I'm just going to do this. Instead of my distribution, I'm going to plot this. Okay, type exactly like this. Okay, I'm going to wait a little bit. Okay, now I want to make this lambda what? Manipulate, right? Let's manipulate. Okay, manipulate this thing. Manipulate what? Manipulate what? Manipulate lambda. Okay. From
Professor, how do you type lambda? Like the symbol?
Escape. LAMBDA escape.
Thank you.
Lambda. Okay. Okay. You can use L if you want. It's just not pretty. Okay. So I want to now lambda. If you look at Wikipedia page, lambda, that's my lambda. Lambda has to be positive, right? It can't be 0. So I have to start, let's say something like from 0.1 to 10. Okay. So it starts with 0.1. So what's the average? 1 over 0.1 is 10. So if I put 10, okay, now it's very hard to see. Okay, the reason it's very hard to see is because it doesn't start at 0. So let's plot this from plot range. Did that work? Plot range from 0 to 1. Anyway, it's not. Now you notice that it doesn't start from 0, okay? Because it's automatically scaled. But watch this. As I increase the lambda, okay, as I increase the lambda, 1 over lambda gets smaller. So it gets shoved closer to 0.
Sorry. Where is the arrow?
Sorry?
Recently? Where is the arrow recently? I think
Arrow.
I saw
I
arrow.
have an arrow.
I mean the arrow plot range, isn't it?
Okay. Plot range was the arrow is automatic. We do this minus and greater sign, it will become an arrow.
Okay.
But don't worry, that's just formatting.
Okay.
Let me show you. Hold on. Good question. Sorry. Plot. See? You can do like plot legend. These are all options. Okay. Plot legend, plot range, filling bottom, that sort of thing. Okay? So these are all little formatting. It's not that. So these are all making things look nice. It's important for your project, I think, to make things look nice. So you can see that this thing here, okay, I can make it move up and down. Now, so this is what's the point of all this? The point of all this is that you get your data first and you plot your histogram. And let's say your histogram looks like this. You fit it with exponential function, but you choose the one that has the nicest fit. You choose the lambda that has the nicest fit. And that's called statistical fitting, right? You fit the model. Now you can make all kind of inference. What's the probability that you have to wait longer than 8 minutes? You can integrate this. Okay. So let's say this is my function. Okay. Let's say my function, okay, is PDF, okay, and PDF and exponential distribution. An average is 0.25. Okay. What does it mean? What does it mean? It means that on average, I have to wait 4 minutes, right? I have to wait 4 minutes. So what I want to do is calculate something like probability x is greater than, okay, x is greater than 5 minutes. Given x is, now I don't know what the symbol for distributed is. So let me go back to special character. Distribute.
อาจารย์ครับ can you show the code above like thank you
Sorry. Okay. See, so let me go with this so you can see that. Okay. Yeah. So it's an exponential. You want to plot PDF of exponential function, exponential distribution with parameter lambda of x. This is the range of x, okay, that you plot. You want to fill to the bottom, or you can do something else like, range plot, whatever, and then you manipulate lambda. So that will be nothing. Okay. Now I want to find the sign that say is distributed. Hold on. I can't find. My bad. Hold on. Let me do this. Let me cheat. Let me go to Okay, and copy this. Okay, this is what I want to do. So, okay, I want to copy this sign. I don't know how to draw it. Ah, distributed. Okay, gotcha. Okay. So I put in my code here. Now, so okay, let me make this bigger. You collect the data. How long you have to wait for the bus? You collect the data, right? And you see that histogram looks like, columns smaller and smaller and smaller. And you decide that the best fit is exponential distribution. And you based on the shape, okay, you decide that 0.25 is the best bet. So 0.25. Okay, now 0.25 is your best parameter, best value for the lambda. With lambda is equal to 0.25, the average waiting time is 1 over 0.25, so that's 4 minutes, right? So if you put a fulcrum under 4 minutes, that's the mean, okay? You put fulcrum under 4 minutes, this is not gonna fall, okay? So average, you wait for 4 minutes. Now, yeah, before we had like a bunch of numbers, right? You can't make any prediction. Now you make this method here. Okay, the method is to use statistical method. Okay, and then you make your application, you make your prediction. I'm going to predict that the probability of waiting more than 6 minutes, okay, by implying that X has PDF exponential distribution 0.25 is sorry. Just a second. F1. Oh, okay. Sorry, my bad. All you need to do is this. X has exponential distribution. What's the probability? So now you actually, and we go to calculus, it's like integrating from 6, this area here, okay, this area here, to infinity has the area 22%. Okay, so what's the probability that you have to wait longer than 6 minutes? Maybe longer than 6 minutes, but less than 8 minutes. You can do all this. Okay? Or
อาจารย์คะ
huh?
Can you repeat how you did the distribution icon symbol?
I forgot. I don't know how to do this. So what I did was I go to this page and I click F1 and I just copy from here. Okay. But actually, the way it's done, it's a special sign. It's backslash distribution. Okay. Now I forgot. I don't know about this shorthand. Yeah, I just looked it up just now. The way I look it up, I go to F1 here, and I copy this sign, this symbol here, and I just put it in the here. This is it. Okay. So I didn't know beforehand either, before this class. I never used this, or I rarely use, so I forgot, right? Doesn't matter, it's on the fly, you can just find it. Okay? So you can also use this thing, escape, this escape. That's a nice one. Let's see if I can do that. Escape, DIST, escape. Good, it works. Okay. So escape is very good. Escape, infinity, escape. What else we have? Escape, DIST. Okay, and a whole bunch of things. Escape, boiler. Yeah, escape EE. Escape EE is exponential. Okay, so memorize it. Escape pi. Okay, so that's it. And these are a few things that you need. Okay, escape EE, escape infinity, escape these. What else we need? That's fine. I think those are special characters that we'll be using. Okay? So now this is how
I
you.
have a question.
Yes, please, louder. I can't hear you.
Okay, the interactive graph above, for me, I have only 2 buttons, which is 0.1 and 10 to click, and I'm not have the slide.
Oh, because this here, notice, this is saying that lambda changes from 0.1 to 10. Now, if you put in extra bracket, it becomes a set, right? It becomes a list. Either 1 or 10.
Okay,
Okay? So if you put something like this, yeah, it becomes a list. Okay? Now, if you do this, notice 0.1 to 10 and 1, you still get this, right? But if you take it out, it becomes from 0.1 to 10 instead of 1.
Okay.
So that's the fun of it.
So I know my mistake. Thank you.
Okay. I think, and this is a tip, by the way, I do a lot of prototyping. For your client, what you want to do is you want to select the parameter that is interesting and put that in the list. So that they don't play with something that doesn't look right or doesn't make sense. You want them to look at special case. If you want to make them look at special case, you can put it in the list. And in this case, you focus on just the 3 case. Okay? But if you want to make it like a software, you do something like this. So this is more general. Okay, so that's the trick. Right. So,
Professor?
huh?
Sorry. So after I put the manipulate function, my graph haven't plotted. It's appear in a table แล้วก็ repeat statement ที่หนูพิมพ์ไปอะว่า plot PDF exponential distribution. I don't know why.
I don't know. Can you show it? There must be some kind of syntax. So basically, what I suggest you do. Okay, try typing with me. Okay, typing exponential. Okay, it suggests exponential distribution, right? I'm going to specify this exponential as a function of lambda. Escape lambda. Escape. Okay. This only tells the computer we are talking about exponential distribution. Okay. I want to plot it, right? I want to plot, but you can plot what? You can plot PDF, you can plot CDF, right? Let's plot PDF. So I'm going to plot PDF of this with respect to X. Okay. So this here, let me not make it really huge. This here say, I'm talking about exponential distribution. I'm talking about this page. Okay. This page has PDF. it has CDF. I don't want to look at CDF. I want to look at PDF, right? So I want to look at PDF. Now I have to name my random variable. Let's just call it X. Okay. So now I want to plot. Now, if I want to plot, comma, I have to specify the range X from 0 to 10, say. Right? Right? Now, I want to turn this guy into buttons. So I put manipulate again, comma, escape, lambda.
อาจารย์ครับ
Yep.
you need a like space like after you type
No,
manipulate
you don't need space.
could it just be one line
Yes, you could. In fact, I always,
Oh.
if it's small, I do one line. If it's, confusing, I make it multiple lines. I make it multiple lines so you can see. But certainly, this is the same thing.
and like does tab matter
No,
so spacing doesn't matter
doesn't matter. The only thing that matter is between two variables, right? A blank B is multiplication. Okay. But you put extra blank here, it doesn't matter. Okay. So if you did this, now the only thing different is that in the plot, I add extra parameter, something like filling bottom. That always makes it look nice. Filling to the bottom tends to be something that makes the graph look nice. Okay, so that's it. But what I want you to understand is the process. The process is this. You take the data. Okay, now I'm going to change, right? And then query. How long to wait for a bus? So record, say 30 bus inter-arrival in minutes. Okay? Say in minutes, okay? And then method, instead of taking this, what's the method? What would it be? You take a plot the histogram. Notice the histogram resemble exponential distribution PDF of an exponential distribution. So try to find best lambda for that exponential distribution. Okay? Say lambda equal to 0.5, i.e. wait on average 4 minutes. Okay? Now, we're not using machine learning right now. Application use PDF of exponential distribution 0.25 or just use this, okay, to make any prediction, i.e. probability you have to wait over 5 minutes. Okay, that's it. So this here, now you learn statistics in your year 1, right? But you probably did not appreciate how it's performed as a step, as a pipeline from data to analysis. This is where the difference between probability and statistical theory and analytics is. In analytics, you focus on analyzing data from the beginning to end, what we call a pipeline. This here, A, B, C, D, E, this is called a pipeline, okay? You feed from data to the histogram to a human being that thinks exponential distribution is best. Next time you want to go to a human being, maybe you go to AI, go to machine learning. But for now, you go to a human being. Human being looks at histogram, decide, exponential distribution. Next thing, go to, what is the free parameter in exponential distribution? Lambda. Okay, let's find the best lambda fit. Now that is actually statistical method, right? By the way, how do you do that? Well, you take an average. In this case, your average was 4 minutes. So your lambda estimate is 1/4, 0.25, okay? So let's make this step. Okay? Let's make this step from the data, the average waiting time is 4 minutes. Therefore, estimate lambda equal to 1 divided by 4 equal to 0.2. Okay? Then you're done. That's your best parametric estimation. This step is called parametric estimation. Okay? Application to make any prediction. Now, in statistics, sometimes they don't use the word prediction. They use the word inference. That's that. That's all you need to know. Okay, so now let me do this. Let me do this. I think I'm going to start to go to a few, not all, a few of the useful ones. Okay, this guy, Bernoulli, okay, this is what? Anybody? It's like head and tail, right? Head and tail with probability P. So Bernoulli distribution is like coin toss, where head, outcome, okay, where x equal to 1 for response. 0 correspond. Okay, that's it. But a coin toss has a 50-50 probability, right? So you don't want 50-50, you want, what do you want? You want P. So P can be 50-50. So let's look at this. Okay. So, yeah. So plot. Okay. Now, let's do this. Let's do the same thing because it's so easy, right? Okay. Yeah. Plot.
I got which section is this?
This is under common distribution. When I say common, I mean the 8, 9 of them, right? 1, 2, 3, 4. Now I count this 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so you notice these are the same 12, right? 1, 2, 3. Okay. Yeah, so that in my case, I put Bernoulli and binomial distribution together. Well, anybody want to know why? Bernoulli is counting the number of heads when you toss the coin once. Binomial is counting the number of heads when you toss the coins independently more than once. Okay, so that's why I put them together here. I should put them together here as well. Now, negative binomial is different. Likewise, uniform and beta, they're kind of like together. And normal and log normal, I shouldn't do that. I should separate. I should put log normal here. And I should put this. Okay, so now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, if you know this, okay, if you know this, you get the beginning of data analytics. Okay, now I don't want to spend my time doing all this, except I want to show you okay. When I say that uniform is a special case of beta distribution, when I do this, what I mean is that Bernoulli is a special case of binomial. Or binomial distribution is a generalization of Bernoulli. Because Bernoulli, you toss the coin once. Binomial is you toss the coin once or more. So one is a special case of the other. In reality, a lot of this relationship, a lot of this distribution are special cases of one another. Okay, uniform, you know what a uniform distribution is? When you go to Excel and you ask for a random number, when you go to Excel, okay, and you type in rand, it's going to give you a number between 0 and 1. Okay. This is always going to be between 0 and 1. It's evenly distributed. But if you don't want you want something between 0 and 1 but not evenly distributed, you go to beta. So this is a special case, this is a general case. Now, this is a special case, this is a general case. Actually, you know what? Exponential is a special case of gamma distribution. So maybe I should put this here. Okay. Okay. Awesome, uniform, log normal. Okay, so let me put this over here. That's it. Okay. Now, the most useful one is obviously this guy. Okay. What I want you to look at, okay. Now, this is what I did in the class, but I want to show one by one. Let's do this. Let's practice. Yeah. Okay, this is simple, right? X squared. Okay, anybody get excited by this? No, right? So I'm going to make it minus x squared. Okay? Now the reason I put bracket here is because I want to put another line. Now, I want you to type with me, escape.
How do you do the power of 2?
Okay,
Like
I'll show
square?
you. Okay. Let me start again, right? So we're gonna plot a few things. We're gonna plot the thing between this x, control, Chinese hat or Vietnamese hat, the thingy, 2. You find it? Control and this upper triangle, this Chinese hat, this Vietnamese hat. 2. Okay. Now,
Mine becomes square root.
It's this guy.
Can you show it again?
Simple. Control plus this symbol.
Oh, I see.
Yep. Okay. So plot x squared, that's not a problem, right? Now, what I want to do is minus x squared. That's not a problem. Okay. Now watch this. I want to plot this and escape, escape. Escape, escape to get exponential, Euler exponential. Control, Vietnamese hat. Now, instead of putting something, you put this whole term. See? Why? Because exponential of something negative is going to be something between 0 and 1. Exponential of something 0 is equal to 1. So now it gets to be that shape, right? Does that look nice? Does that look nice? This is the normal shape. This is the normal shape. So let's just plot this. See, it's normal shape. Now, is this normal distribution yet? You learn from your probability statistics class that the area has to be 1, right? So let's try this. Let's try this. Let's integrate this function of x between escape infinity minus 2 infinity. See what we got. Square root of pi. So what this tells me is what? Does not integrate to 1, right? How do you make it integrate to 1? You divide, right? The whole thing. Okay, or control backslash, right? Now it integrates to 1. This is your standard normal distribution. Okay, so if I plot this, okay, plot this, okay, and I also plot this, PDF of normal distribution standard x. Looks exactly the same. Oops, except this thing doesn't start from 0. So let's put them together. So
Professor, how to do the distribution symbol?
okay, just a second. For some weird reason, it doesn't. Just a second, I kind of have something wrong here. Anyway, okay. Distribution is escape, DIST, escape. Something weird here. I did something wrong. I have to get back to you, but for some reason, it should be the same line. It should be on top of one. Anyways, let's look at the one that I prepared earlier. So these are basically it. All the function to create that. So this is your normal distribution. Now, I want you to recall two things. 6. Obviously, the normal distribution is ubiquitous. But why? 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 Because a lot of things converges to that shape. What do I mean by that? This doesn't mean anything. Let's say if I want X to be any kind of distribution, okay? There is a mathematical result. Say X, okay, is this, okay? Let's say some kind of funny distribution. Okay, X is funny distribution. Okay, it can look weird shape, all kind of weird shape. The point is what's called center limit theorem says an average independent identically distributed xi, okay, say x1 plus x2 plus x3 plus xn, where n gets close to 30, will be normally will converge to normal distribution. Okay, so let's say if X is funny distribution, okay, with mean A, okay, then sum of n b xi will have normal distribution with mean NA. Okay, so if you change from sum to average, you have this. Okay, so why do you think you see normal distribution all the time? Because, so you see distribution all the time because, answer, because of central limit theorem. Okay. X is, okay, I'm not going to say central limit theorem here, just say CLT. Now, this happens in two ways. A, in statistical method, you gather IID sample, okay, of size n is greater than equal to more. Okay. 2, B, in life, a lot of random value comes from adding or averaging micro random events. Okay, so this is a formal way of things happening. Okay, central limit theorem means that you have X that has any kind of distribution. Okay, now to emphasize the point, let's do this. And this is a little bit hard for you to do now, but yeah, and this would be very insightful. Okay, now. So let's go to this, where's the, yeah, this is my histogram, okay, of Geyser, right? This is waiting time, right? Watch this, okay? Now, based on this data, I can do what's called empirical distribution. What does empirical distribution mean? It means instead of fitting the mathematical function, I'm just going to take the histogram as a PDF. I can do that. Let me show you, okay? This is a little bit tricky. Okay? Empirical distribution of this data. Okay, so I'm going to call it empirical faithful duration distribution. Okay, empirical faithful duration distribution is equal to this, and this is a mathematical function. We do it in Mathematica. So I'm going to do this first. Okay, now this has internal mathematical function, but that mathematical function you don't know what it's like. So I'm going to random. Okay, I'm going to randomize from it. Random variate from this. Okay, let's take 5. Okay, notice what happened. If I take 5, I get some that's here, maybe here, maybe here. It looks just like this one. See, there's no trees. So if I get about 30 of them, okay, if I get about 30 of them, and I do a list plot, see, there's a lot of 4s, a lot of 2s, not a lot of 1. So it looks realistic, right? Now, so what if I do this, okay, and divide by say 30, okay, and I add total. Total and divide by 30. Okay, oh, so and take an average. Sorry, it's easy. Okay. Okay. It gets to 3.75. Now remember, what is the mean? What is the mean of this thing? What's the mean of this? What's the mean of this thing? It's about here, right? Remember we did that before. Now, watch this. Okay. Now, if I did this, okay, my CLT demo is equal to table. Take this and take 100 of it. Now let's take 1,000. Okay. Okay. Guess what happened when I look at the histogram? See that? Okay, that is the magic of central limit theorem. The normal number looks kind of like around 2 or around 4, but if you take 30 of them at a time, the distribution of the average is called sampling distribution, approaches the normal shape. Okay, now Mathematica is so smart that it can do this. Find distribution of this. Normal distribution.
Can you scroll up a little bit?
Okay.
Thank you so much.
What I did was pretend. This is how I pretend. I pretend that I have a mathematical function called empirical distribution that takes the histogram. Remember I told you that if you take a histogram and you make a mathematical function, you can do some kind of prediction. Well, this is kind of like back to basic. I don't want to fit the mathematical function. I want to use the histogram as the distribution. So no generalization whatsoever. This is a bad practice in real life, right? Because in practice you want to generalize, but you can do it. You can do it. You can pretend that nature is exactly as your data set. That's called empirical data. Empirical distribution created from that. I generate, this is called random variate, generate some random number from that distribution, generate 30 of them at the same time, takes an average, and I know that the distribution of this thing should approach normal distribution. So I just make a table of 10 of 1,000 of them and I plot. It would look even nicer if I add more samples. The histogram would look even smoother, I think. Okay. This looks virtually indistinguishable from normal distribution. And just to confirm, I asked Mathematica. Now, Mathematica is even more intelligent. Remember I told you the loop was, you look at the time you wait for the bus, and you say to yourself, ah, that looks like exponential distribution. Well, Mathematica has an AI that does that. Well, not quite an AI, but yeah. More like CI, computational intelligence. It searched over the fit and it would find the best one. In this case, let's find the best one. The best one is actually this thing. Normal distribution with mean 3.48, and this is a sigma. Now, you know normal distribution has 2 parameters, right? This controls the standard deviation. I'm not going to review that. Okay. So definitely,